Okay, this video will address kinetic energy when something is rotating, right? So when if I take an object here, okay, and if it's let's say a sphere, a ball, basically, right? And as it's rolling and traveling to my right, the center of mass is right there, and this center of mass never rotates. It just translates, just moves as if it's not aware of rotation, basically. But every other point on the sphere or the object that's rolling has some angular velocity, right? So that's what we're going to do here. So we're going to be looking at two kinds of energy here. We're going to be looking at translational and rotational kinetic energy. Now the formula for rotational kinetic energy, I guess we'll call it K rot, is 1/2 I omega squared. Same analogy with translational kinetic energy, which was 1/2. The I plays the role of M and omega plays the role of V. But just keep in mind that when something is rolling, you have both. You have the center of mass that's not aware of any rotation, that's translation, and you have the object itself, every other part of the object that's spinning. All right. Now, I'm going to do a shortcut here to show you there is a relationship between rotational kinetic energy and translational for some objects. So I'm going to take a sphere or a hoop, and I'll do it for all the other ones. So rotational kinetic energy for a hoop is not filled in. It's 1/2. I for a hoop is mr squared, and V is r omega. This is the V for the center of mass. And you can see that omega is V over r, and you have to square both. So this is gone. Okay? So in here, you can see that K rotational is equal to K translational. Okay? Okay, so let's try for a filled-in disk. Okay? Now, for a filled-in disk, you have a half here. So if I take this half here and I put this half here, which is the same half basically, okay, you can see that for a sphere, I'm gonna have a half in here. If I do this for a disk, not a sphere. If I do this for a sphere, I'm gonna have 2/5. So if I take the 2/5 here and I put the 1/2 here, and I'm putting the 1/2 inside to end up with 1/2 mv squared, to end up with translational kinetic energy. So this is going to be 2/5. Okay. So basically, for our three mostly used shapes, the kinetic rotational energy is going to be that number, that coefficient for the moment of inertia times the K translational, right? And this is pretty powerful here. So we don't have to prove this all the time. All right, so let's try some examples. I'm going to go right to some examples. So I'm going to do an example with a pulley using rotation, because in the past when we did pulleys, we ignored the mass of the pulley itself. And that was still challenging, but now it's just like an extra dimension. And then we're going to do something going up a ramp. So this is number 55 in your packet on page 35. So I have a pulley that has a radius of 0.26 meters, and it has a mass of 7.5 kilograms. You know what? I'll make this capital M, because I like to make the pulley different. And then I have two objects. And this is the ground. So initially, they are in this position here. So initially, this is 1, this is 2. And then you're going to release them. And this 2 is heavier. Okay. So it has a mass of, well, I'm going to label it as 2 here. So 26.5 kilograms. 1 has a mass of 18. Okay. So there is some tension here. This is tension to T2, T1. This is 265 newtons. This is 180 newtons. But we're going to do this with energy. We're not going to use any rotational dynamics. So the question is asking if the system is now released, use conservation of energy to determine the speed of M2 just before it strikes the ground. So later on, this picture will be like this M2 will be on the floor and the other one will be up. So I'm going to start looking at the amount of energy that this whole system has before we release. So it looks, or at the moment we release. So it looks like we're going to have mass 2 is going to have some gravitational potential energy. Okay, and that's all the energy you have. Now, that energy is going to be converted into energy in M1, gravitational potential in M1, M1GH, plus, now when you release them, this 2 is going to move and 1 is going to move. But they're both going to move at the same speed. So I think we can combine their kinetic energies. So in other words, we're going to be looking at 1/2 m1 v squared plus 1/2 m2 v squared. So I think I can put them together since they're moving at the same speed. Plus the energy, okay, used up to rotate the sphere itself, and that's going to be 1/2 I omega squared. And I think we're going to use that quick shortcut. Well, maybe we yeah, maybe we can try to use the shortcut. So let's try that. The I, so this is, I think, going to be just 1/2 of 1/2 the mass of the sphere, or this disk, the pulley, times v squared. Yeah. Okay. Yeah, that's what I have. All right, so now it's just a matter of plugging numbers in. So M2 times G, so that's 265 times 3 meters above the ground equals 180. Now when this drops 3 meters, this one is going to go up 3 meters. Plus 1/2 times, if you combine those masses, we should get 44.5 v squared plus, I guess we can make that 1/4, 7.5 v squared. And we just have to solve for v, and the v is going to be 3.25 meters per second. Okay. So now we're going to try to do one with an object going up a ramp or down a ramp, it doesn't matter. So I'm going to make an object go up a ramp. Okay. Okay. So let's just make that object, I don't know, we can start maybe with a sphere. And now it's we're going to find out that the mass doesn't matter and the radius of that sphere doesn't matter. So I'm just going to call him R, and I'm going to give it a mass M. And initially it's rotating, and it's the center of mass is just sliding. It never kind of like changes that height. It never rotates. And we're going to try to figure out how high is it going to go up this ramp if the angle here is 30 degrees. What's the highest point that it's going to reach? We're going to do conservation of energy. Initially, this sphere has translational kinetic energy, which is 1/2 m v squared, and it also has rotational. And if we follow that shortcut that I showed you, I think it's just going to be 2/5 of the translational kinetic energy, 1/2 m v squared. You can write it as 1/2 I omega squared, but you're going to find out that it's same thing as writing it like that. Equals, when it's at the highest point, it stopped sliding up the ramp and it stopped rotating. So there is really no kinetic energy at the highest point. So you only have gravitational potential energy, mg h. Okay, so here is your mass, it's gone. Okay, and that's what we did when we did the moment of inertia. We had things sliding or rolling down ramps. The mass and the radius didn't matter. Okay, so this is going to be, let's see what we have here. 1/2 v squared plus, I guess we can say that's 1/5 v squared equals 10h. So 1/2, so that's going to be 7/10 v squared. And so v is going to, oh, actually we're looking for h. So h is going to be 7/100 v squared. So depending on what speed you had initially, a linear speed, you can figure out your maximum height. So I think the maximum height, I'm going to write it here, is going to be 7/100 over v, I mean times v. I'm going to make this initial v. Okay? Okay. Now the next question is, well, how fast is he going to be going when it's only, I don't know, maybe we'll say like a third of the way up. So this is a third of h max. So I want to know its linear speed at this moment here. I want to find this v. Right? So I should not have erased this, but anyway. So it's initially it has this translational kinetic energy. It has this much rotational kinetic energy. Okay? And now when it's up at this point here, it has three forms of energy. It has your gravitational, so that's going to be 1/3 h max. Okay? And here you can plug in numbers. I mean, if I give you a VO, you should be able to solve. Plus, it has translational kinetic energy, and it has rotational. So it's still spinning as it's going up. So 2/5, 1/2 m v squared. So I think we can. I think we came up with this to be 7/10 VO squared. That's going to be equal to, I think, after we cross out the masses, of course. Okay. Last one, I think, is going to be also 7/10 v squared. And then I'm going to replace this h max here. So it's going to be g times 1/3 times 7/100 v initial squared. So I think if I make this a 10, I can cross out that 0 from there. So this is going to be 7/30. So if we subtract here, so if we make this over 30, we make this 21. So that looks like it's going to be 14/30, which I think can be reduced to 7/15 VO squared equals, I could have crossed out the 7s actually, equals 7/10 v squared. So get rid of this 7, we'll leave it as a 1 in there, and put this 10 up here, and reduce it to 2/3. Right. So which means V is going to be VO times radical of that. Okay, at that location there. Now the next question is, if I replace this sphere with a hoop, right? Okay. Will it go higher or lower? Now, if I do it for a hoop, and I'll do it with the math and I'll explain it conceptually. If I do it with the hoop, I will have 1/2 mv squared plus the coefficient for the hoop is just 1, so it's going to be another half mv squared, this is initial, equals mg h when you get up to the top. There's no kinetic energy. So I think we can get rid of the masses. Okay, we can just make this 1/2 and 1/2 1, and we can divide by h. Okay, I'm sorry, we're forgot it. divided by 10, I think was, yeah, divided by 10. Now, if we compare this to, well, I can make this 10 over 100 to see that we can compare it easily. It looks like this number here is greater than 7 over 100 V initial square, which means the hoop is going to go higher. That's probably counterintuitive because you're probably thinking the hoop has a higher rotational mass, so it's lazier to rotate. But the trick is, in order to get this hoop to have an initial speed of VO at the bottom, a lot of work was put behind it to get it up to that speed because of that laziness. So the hoop has more energy at the bottom of the ramp when it first started. So that's why it's going to go higher. So the hoop is going to go higher. So I hope that makes sense. And the trick here is a lot of more energy has to be put in behind the hoop to get it up to that same speed as the sphere. Okay? All right. Thank you.